Hello everyone, welcome back to Calculus 1, and this time we will continue section 3.3, differentiation rule. And indeed, so far we only talk about one rule, the power rule or power rule. Okay, derivative of a single power function, it is r times x to the r minus 1. And this is really the only rule we talked about. But I still want to say power rule, it is the most commonly used rule and do consider it is the most powerful rule. But you may want to know it is very restrictive. The power rule only can be applied to some very single power functions, to a very single power function. But still, it is powerful because we do recognize this power could be some simple integers, positive integers, and also it could be negative integers. And also, I want to know many times you see some function like 1 over x squared 1 over x. Well, they kind of like power functions, but to be precise, okay, 1 over x squared is not a power function, but when you convert 1 over x squared into x to the negative 2, that is a power function. Similarly, 1 over x is considered as x to the negative 1. And also square root of x, we cannot jump inside the radical notation to calculate the derivative. But with the power rule, what we can do here is the square root of x can be converted into x to the 1/2. Then we get a derivative. And also another example, 1 over square root of x. Again, we cannot jump to the denominator. Okay, so square root of x is x to the 1/2. And with this entire thing in the denominator, it simply means x to the negative 1/2. Then we get the derivative. That is about the power rule. It is very powerful, yet very limited. And many times we may not just have a single power function. We may have a combination of power functions. So this time I'm talking about the sum rule. Let's read it from this line here. Maybe just read the plus first. Okay, plus sign first. So from the left, I'm saying this means the derivative of the sum of two functions. I'm reading the plus sign first. And then to the right, it is the sum of two derivatives. Together, it simply says derivative of a sum is the sum of two derivatives. Similarly, derivative of difference is the difference of derivatives. For example, if we consider the derivative of x to the 5th power plus x to the 11th power, well, these are individual power functions. But anyway, together, we cannot handle derivative. So precisely what I did, according to the sum rule, I separate those into two derivatives. And then for each, I use the power rule. The next one might be a little tricky. Still, they look like power functions. But anyway, first of all, according to the sum rule, I separate those two derivatives into those two functions into two derivatives sum into two derivatives, sum of two derivatives. Certainly, x part is easy. 1 over x, to get a derivative, you are going to consider this as x to the negative 1. And x to the negative 1, actually, we did have the calculation derivative 1 over x right here, x to the negative 1. So I just copied the result directly from there. Together, it tends to be 1 minus 1 over x squared. The next one, make sure you know sum rule. I usually just do the sum rule and the difference rule together because really the same thing. Okay, derivative of the difference of those two functions, it is difference of two derivatives. Not a lot to say about x squared. It can be handled directly. But for 1 over x squared, it is converted into x to the negative 2. 1 over x squared is not a power function. X to the negative 2 Yes. Okay. So accordingly, we have derivative 2x. Bring down this negative 2 as a coefficient, but there's another minus in the front, so I do have plus 2. Plus 2. Then decrease this negative 2 by 1. That turns to be x to negative 3, which means x to 3 in the denominator. That's the derivative. Sum and the difference rule together. And also we have the constant multiple rule. This is the constant multiple rule I'm talking about. To the left, I say that is the derivative of a constant times function. To the right, it is constant times derivative. Together, it is simply saying the derivative of a constant times function is constant times the derivative. So I still have two examples. Derivative of negative 10 times x to the 7. So it is negative 10 times the derivative part of x to the 7, 7x6. Together, simplified answer, negative 70 times x to the 6. Derivative 5 over square root of x, it's 5 times 1 over square root of x. Right? This time square root of x besides square root of x in the denominator. So really the function part, it is x to the negative 1/2 as a power function, okay. Then we calculate a derivative. This is 5 stays. Bring down this negative 1/2. I have 5 combined, negative 5 over 2. Negative 1/2 decreased by 1. So that's a negative 3/2. Negative 3/2, right? And so negative 5 over 2 stays. X to the negative 3/2, you can consider this as x to the 3/2. X to the 3/2 further can be simplified as x times square root of x. So I'm going to leave that to you if you are really convinced how I get x to the negative 3/2 as x times square root of x in the denominator. Sum rule and the constant multiple rule. And now I'm saying, look at these examples. Certainly, I believe we can do a little more work about the derivatives, right? We can handle a little more functions for derivatives. So the next example, it is from the textbook, checkpoint 3.14, derivative of a function, a cubic polynomial, third degree polynomial. There are 3 terms. The sum rule and the constant multiple rule basically allows us to calculate the derivative for those individual power functions. But keep in mind that those individual power functions cannot be in the denominator, cannot be inside the radical notation, okay? Only for the sum, difference, and the constant multiple those cases. So accordingly, we get a derivative here. It is 2 times 3x squared, 6 times 2x plus derivative from this 3. Remember, derivative constant is 0. So this is derivative I get. And also, let's do one more example before we take a break. Checkpoint 3.15, it is the one from the textbook. This is kind of old kind of question. Remember, we said that derivative, it is the instantaneous rate of change, and indeed, which is the slope of the tangent. So this time, we need to find out the equation of the tangent line to the graph of a function at x equal 2. So to handle the equation of line, I would say the most popular choice would be the point slope form. Or I think a slope intercept form is popular too. But anyway, I guess maybe point slope form is more convenient. Okay, it only requires any point requires one, well, any point really, that's what I'm saying, and the slope. So clearly, for the given point, we need to consider here it is x naught equals 2. Accordingly, y naught would be f of 2, which really means plugging 2 for x into this original function. And the double check with my numbers, looks like I should be fine, right? 11. And then I'm still considering this point slope form. Looks like we need to handle the slope. Remember, slope is a derivative. So I calculated the derivative. And to this moment, I hope you see this really would be the slope at any value of x. So specifically at x equal 2, we have the specific slope. Replace x with 2. So we got a 12. And then finally, the equation of the tangent line using the so-called point slope form right here, it tends to be such. And also, as I mentioned, if you really like the slope intercept form, you can further simplify or convert it into the slope intercept form by multiplying this out. And don't forget to move this one to the right. This is minus 24, add 1, minus 23. I believe I should be all right. So really, so far, I would say in 3.3, we covered the 3 rules. The power rule right here. And also, we have the sum and the difference rule. Sum and the differential rule, they should be considered a single rule. That's the same thing. And then the constant multiple rule. And it does, well, altogether, it does let us, they do let us to handle many different functions. But anyway, they will always have to be generated from power functions. We do have a lot of functions not from power functions. So I want to introduce one rule very quickly. Hopefully it's simple and easy. Derivative of the exponential function, derivative e to the x, it is e to the x. And keep in mind, this is very simple and easy, and indeed it is true. Whenever someone says, when you have a function such that a derivative is itself, it has to be this function. It has to be the exponential function right here, nothing else. So this is section 3.3 about derivative rules. Now we have the power rule, the sum rule, the constant multiple rule, and derivative for the exponential function. Let's take a break before we continue. Thank you for watching.